I want to provide some of the theoretical background and some formalization of reinforcement learning. The information in the slides is based on this fantastic book on reinforcement learning by Sutton and Bartow, and it's available online for free. You can also buy a copy. But it's kind of like the book on reinforcement learning. It's being cited by many, many people. Okay, so let's talk a little bit about what we have. We have an agent, we have an environment, and the agent interacts with the environment, and we have discrete time steps, so no continuous time. We have a set of states, and then we have a set of actions available in a particular state. Now, in our world that we have seen last time, the actions are always the same, up, down, left, and right, but we can imagine that in different states, there are different actions. So think back to the agent, to the programming assignment that in some states we might be able to clean. I mean, theoretically speaking, we're able to clean in all states, but maybe we only want to do that in states that are actually dirty. So at each time step t, the agent receives some representation of the environment state, st, and on that basis, the agent selects an action that is available to it at that state. So diagrammatically speaking, again, this figure is from the Sutton and Bartow, figure 3.1. We have an agent, we have an environment. The agent takes an action. And again, not all actions always work out. There's typically some sort of stochastic transition model. And we end up in a new state. And that new state gives us a reward. And so based on this new state and the reward, the agent decides to perform another action at the new time t. So that's kind of like the basic idea. We talked a little bit about returns last time, and I mentioned that I was going to go into more details this time. So let's do that. And so at each time step, the reward is some typically small number. And so the idea is we can sort of like look at what the agent is doing at different time steps. And so in essence, we're going to have a sequence of rewards. So what we want to do is we really want to maximize the expected return. Okay? So the sequence of rewards, again, typically there is a big reward somewhere at the end. But again, if there's a way to get to that big reward with different, by going through different states that have perhaps slightly higher rewards than other states, that certainly would be preferable. So again, it's the expected return because things don't always work out, but we want to maximize it. Again, if there is a final time step, then this formula here captures the entire reward. Now, sometimes there is not a final time steps. So I talked about, say, graduation, from college. So you put a lot of effort into things, into your classes, and sometimes the rewards are positive, sometimes they're not necessarily positive. But that diploma or that nice job that you're going to be getting is that final reward, right? But that doesn't mean that life ends. So perhaps we want to think of them as episodes. So right now you're in college, and so you're sort of like working towards that goal of getting that degree and that really nice engineering job. So that's kind of like what we're going to be doing here. Now, so I talked about episodes. So the other thing we talked a little bit about is this tuning factor called discounting. And so it's the idea about how much attention are we going to pay to that final reward and how much attention are we going to pay to the immediate reward. Again, the final reward might not always happen. Hopefully it does. And sometimes we just need to do something. So the discount rate, here's how it works. We get the immediate reward here of our action, and then the future reward, again, it's a stochastic transition function, will multiply with this discount rate. And then the future of that one, we square discount rate, and so on and so forth. So we triple it, quadruple it. So that's how we're going to calculate the reward. And so we can, make it just a little bit less than 1. We can make it 0. So what happens if we make it 0? If we make it 0, the agent is what we call very myopic. It's only concerned about maximizing its immediate reward. Okay. And as it approaches 1, the agent takes future rewards into account more strongly. So the agent becomes more farsighted. That's kind of like what we're dealing with here. So as I've mentioned to you before, in our exercise here, a lot of times we have that gamma set to 0.9. All right, very good. So now let's talk a little bit about Markov. So the Markov property is named after a Russian mathematician who lived a bit ago. And so at a certain state, we sort of look at what information is available to us or to the agent. So we can sort of look at the immediate measurements, such as sensory measurements. And so the question is, to which degree do we need to look at past sensations? Okay, so perhaps the state signal might summarize past sensation and in the way that all relevant information is retained. So perhaps we want to keep history around. Now, if we're able to do that, if the state signal keeps everything, all pertinent information around, then we said that it has the Markov property. It's said to be Markov. Let's look at some examples. So for example, in checker, it doesn't matter how we got to a certain position. All that matters is the position, obviously, whose term it is. It summarizes or captures everything that's important about what needs to happen next. Okay. Again, it doesn't matter how we got there. My favorite here is, a cannonball, right? It happens to us all the time. The current position and velocity of a cannonball is all that matters for its future flight, right? It doesn't matter where it came from and how it got there. And so sometimes it's called as the independence of path property. Yeah, what you want to do is duck, right? So let's have a look at something that doesn't have the Markov property. So again, what we're interested in is how should we respond at time t of t plus 1. So what should we do next, right? And we're certainly at time t right now. So in the non-Markov case, this response to depends on everything that happened earlier. So what we have over here is we're looking at the situation that we're going to be in, that's going to be S prime, and the reward that we're going to be getting as part of our action. And it depends on the entire sequence, right? What we did initially, what the initial state was, the reward we got, all the way up to current 1, right? The reward we got, the action we took, and the state that we took. And so what we have to have over here is we have to have a complete history of everything we have done. So if that is necessary, then no, this one does not satisfy the Markov property. The Markov property is satisfied when we have this sort of situation. We can make a decision that is based only on the current state and the action that led us there. And it's going to give us a reward in the next state, and it's going to get us into a certain state. So that's when we have Markov property. And that's kind of like very important for us when we do reinforcement learning. As you have seen in when we looked at value iteration, that's what we did. Now we looked only at the current state, at the actions that are available to us, and so made a good choice. So a reinforcement learning task that satisfies the Markov property is called the Markov decision process, or MDP. If the state and action spaces are finite, kind of like something that we're interested in, then we have a finite Markov decision process. And so they're very important to us when it comes to reinforcement learning. So what we have over here, we talk about the probabilities of a next state. So let's explain this expression over here. We again have an action A that we took to get here, state S that got us here. And so we're interested in what is the probability that we're in S prime at t plus 1. And it depends on the action that we're taking. Our transition model, obviously, is involved here, the current state. And so we're interested in the state transition from S to S prime. So the expected value is obviously very much related to this thing. And the reward, again, we're sort of looking at, okay, we have a certain action that got us here, a certain state that got us here, and then we ended up, or we will end up in t+1 in state S prime, which will give us a reward RT plus 1, so the reward of next time. So what's the expectation of that? That's what we're interested in over here. All right, so a little bit of background of Markov decision processes. Up next, we're going to talk about policy iteration. I'll talk to you then. Bye.